Hello there, this is exercise 3A.1. It's our first look at the Poisson distribution, probably in year 12 further maths, but could easily be done in year 13 as well. Now, the Poisson distribution, named after a guy called Simeon Poisson, who was a French mathematician who looked at a lot of situations where probabilities needed to be found. And so he came up with this, what's called now the Poisson distribution. And I would describe these as generally being quite rare events, things that don't happen very often. And so, for instance, an exam question I saw was you're driving along a road looking for dead snakes. It might be your job to go and collect them and get them off the road. You probably don't find many dead snakes if you're living in the UK, but you might do if you was living in I don't know, near Las Vegas in America or something like this. Now, so these rare events, and this, for instance, you kind of you're able to use what we now know as the Poisson distribution if certain things apply. So I've described them as being rare events, but they might not be quite so obvious. And so we have these three rules, and we call them conditions for the Poisson distribution to be used as a suitable model, sometimes called assumptions. So these three rules are, well, here they are. Number one, the events occur randomly. So if you talk about that dead snakes as we drive along the road, that's the space bit, I suppose. We wouldn't, there's no reason for them to all be in one place or another place. They're completely randomly spaced out. Number two, each, in this case, event, dead snakes or whatever we're looking at, each event occurs independently. Just because one occurs doesn't make another one occurring any more or less likely. And the third one is called the constant average rate. Now this is actually given a symbol. We call it lambda. And lambda, the constant average rate, well, in the case of my dodgy example from just now, is, for instance, if I drive along the road, on every mile I drive along the road, I might expect to see 2 dead snakes or 3 dead snakes for every mile. If it was that, I talked also about the telephone call situation, and you might, for instance, have someone sat at a telephone exchange, and on that telephone exchange, perhaps in any hour, they don't expect many calls. They might only expect, say, 4 or 5 calls an hour. Might be really important. It might be, one of these help telephone lines where people ring up asking for help. Now, if that's the case, it's deadly important. But the point being, you don't know when they're going to occur. You might know that on average you get, say, 5 an hour. The constant average rate would imply that there's no particular day, for instance, when it's higher or lower. So again, you might have to bear this in mind. If I was working the night shift, I might know, for instance, between 10 and 12 every night. There's lots of these things, and most other times there's no telephone calls or very few. Now that wouldn't be a constant average rate, so that wouldn't be applicable using the Poisson distribution. So you've got to be careful of these three. If you're going to use the Poisson distribution, how reasonable are they to assume that the events are random, that the events are independent, and that they occur at a constant average rate? All right, let's assume these three things do apply. And when I talk about these three things, by the way, you just be aware that you are often asked to state these three conditions in the exam. So just bear that in mind. You need to remember these. So let's go back to this idea that let's assume that they are true. It might even be, for instance, they tell us that x, now this is the way you write it, x is Poisson. It's distributed Poisson. Oh, and I also need this constant average rate. So I was talking about then, perhaps as I drive along the road, every mile I see 3 snakes. I expect to see 3 snakes. That's the average constant rate that I'd expect to see them. So I can find this using a formula, and Simeon Poisson came up with this formula to predict this. Now notice what you write. You might write, for instance, the probability that x, the number of snakes I see, is, I don't know, we expect to see 3, but maybe I want to know, well, what's the chance of me seeing only 2? And you chuck into the formula. You go e to the minus, and what's lambda? Now lambda, remember, is the number I'm expecting to see. So I'm expecting to see 3, and I want to know, well, if I'm expecting to see 3, what's the chance I'll only see 2? So I go e to the minus 3 times by. Now, lambda appears again. It's 3 to the power of x. What was x? X was 2. 3 squared divided by 2 factorial. Now, you should remember this 2 factorial means 1 times 2. And if it was 3 factorial, it would be 1 times 2 times 3. If it was 28 factorial, it would be 1 times 2 times 3, all the way up to 28. But anyway, my calculator will work that out perfectly well. So I'm just going to type it in. It says e to the minus 3. So e to the negative 3 times by 3 to the power 2, well, that's 9, or you can type it in 3 to the power 2, divided by 2 factorial. And 2 factorial, there's a button on your calculator for that. Or you can just know that 1 times 2 is 2, so you just divide by 2. Anyway, I get 0.22 there, 0.224. So in my example, which I've just made up, 0.224 seems to be the probability of doing it. And these are the kind of things we have to do all the time. I'll just clear the screen just so that we can just make good notes. So where lambda is the constant average rate, so I'd recommend you copy down this formula, where lambda is the constant average rate, or mean, sometimes called the mean, or the expected amount that you'd expect to get. We write x is distributed as a Poisson distribution, lambda, or x as a Poisson distribution with mean lambda, perhaps. So all these ways mean effectively the same thing. Notice that formula. The formula is in the formula book, but we need to know it. We need to know it. So I recommend you learn that. Okay, so now we know the formula, let's do a question. Well, in fact, I need to point this out. The mean and variance of a Poisson distribution, this is a strange phenomenon. Normally, when you get a set of numbers, you can calculate the mean, you can then calculate the variance. You do this on your calculator dead easily. You might remember that the variance is the standard deviation squared. And it talks about the spread of the data. And this talks about kind of where the middle of the data is. Now, weirdly, the mean and the variance of a Poisson distribution are the same. Now, it only is true for a Poisson distribution. It's one of those things that we're meant to know. So it's just a general idea of another thing that kind of lets you have a clue that it might be Poisson. So I might have a situation where I'm looking at the data and I find the mean, and I find the variance, and I think, oh, I bet they're very similar. Maybe the Poisson distribution is appropriate to use. That might save a lot of time as well later on. Anyway, so basically using the symbols, notice the mean here. Now normally the mean is referred to as mu, like this, mu like this. This is the population mean. And it could be written E of x as well, what I expect to get, but notice I've called it lambda. And in this case as well, the variance, which is again usually sigma squared, I'm saying no, it's lambda. So it's because of this, the mean and the variance are the same. So make sure you've written that down, please. And here's my first question then. So it says the number of telephone calls x to a telephone exchange has a Poisson distribution. Notice it says it's Poisson. I can immediately write x is Poisson. You always write this PO. With mean 2, now again, you always put that in a bracket, 2 like that. And this is the standard notation. And it says find the probability. I know we're expecting to get 2, find the probability we only get 1. And again, we've seen how to do this. You can use the formula e to the minus, well, what's lambda? Lambda is 2. And what's our x? X is the number here. Oh, x is 1. So just writing those down so I can write it and refer to it. So into my formula, lambda to the minus, e to the minus 2 times lambda to the x, 2 to the 1 over 1 factorial. And I just type it into my calculator. E to the minus 2. Very similar to what we just typed in. So times by 2 to the 1. 2 to the 1, that's 2, that's easy enough. Divided by 1 factorial. 1 factorial, if you think about it, is 1. So I get 0.271. Actually, I get 27067 and so on and so on. But I've rounded it to 3 significant figures. Let's see what the answer is. Oh, before I do this, actually, I should say to you, there's a better way of doing it. 271 will be right, I'm sure, but look, on the Classwiz, this is a great calculator. I recommend you use it, one or similar one. I'm sure there's other great calculators. But on the Classwiz, if you press, and you'll have to type this in, the menu button, and the menu button is this one here, and then you say 7 and then press down, and what you'll notice, if you don't press down, it says normal CD, normal PD, normal CD, and then binomial PD. Now we don't want any of those. We want the ones that say Poisson. So that's why you have to press the down button, and then it comes up binomial CD, then it's Poisson PD, and it's Poisson CD. Now, Poisson PD is the one I want. So if you ever want the probability that x is equal to a number, we're going to use Poisson PD. PD represents, or stands for rather, probability distribution. So this is the Poisson probability distribution. And basically, whenever it's equal to that, you use PD. So I can do this. If you, when you type this in, menu 7, go down to Poisson PD, and then press variable. There's two options: there's list and there's variable. Personally, I never use list. I always use variable. And then you type in the two things you need. It says x equals 1 and lambda is 2. And of course, we saw that before. X equals 1 and lambda is 2. And it tells you what to do. And you press go. And sure enough, it does say the answer is 0.2707 and a bit. So that's how you get the calculator to do the work. And we're going to try to do that as much as possible. Notice this one's slightly different, actually. It still says it's a Poisson distribution. It still says mean to. So it's the same question. But now, rather than using, now do you remember when I said, if it ever says Poisson, probability x is equal to a number, I said we're going to use Poisson PD. And if it ever says the probability x is less than or equal to a number instead, we're going to use Poisson, and this is where we use the CD button. So now what it actually means, of course, is x is less than or equal to 4. So that would be, well, it could be equal to 0, it could be equal to 1, I could get 2 calls, I could get 3 calls, I could get 4 calls. It says less than or equal to 2, yeah, so I could get 4, but I can't get any more. So I would have to work out, using this formula, that probability and this probability, and that's 5 probabilities to work out, and I don't want to have to do that. So instead, I'm going to cheat again on my calculator. The Classwiz lets me do this. And this, as I said to you, is actually what we do. We press Poisson CD. So menu 7 again, it's exactly the same. Menu 7, you press down, you press the Poisson CD this time. The calculator knows Poisson CD means less than or equal to. So I press variable, x is 4, lambda is 2. And CD basically means cumulative distribution, adds up all these probabilities as it goes along. And if you type those in, according to me, I get 9473. So hopefully when you do that, to 3 sig figs, 947 of course, but the calculator tells me loads of detail if I want it. Third version of this. Now this is interesting. Now remember before we wanted I could draw this on a number line almost. 0 calls in an hour, 1 call, 2 call, 3 calls, 4 calls. After a while, you get bored of writing this. This goes up to infinity eventually. I could get 500,000 calls in an hour. Hope not. But you get the idea that what I want here, of course, is the probability that x is greater than or equal to 2. Now that's all these. I'd have to work out all these probabilities. And the problem is there isn't a button on my calculator, on this Classwiz calculator at least, to do this for us. So we need a little trick. And the way we do it is, see, there is a button that does less than number. And I don't want 0 and I don't want 1. I want all the others. And then the trick is to do 1 minus the probability that x is less than or equal to, not 2, but 1. Because I want 2 and upwards. So I do that. So I don't want 0, I don't want 1, I want all the others. So to do this, again, I'm going to cheat on my calculator. I'm going to do Poisson CD. I have to type this into my calculator and then do 1 minus at the end. So when I do this, I reckon when I do it, I get the final answer of 0.5940. So presumably when you type it in, when you type this Poisson CD or menu 7 and things like that, you get 0.3060. And when you do the 1 minus, you finally get this answer. Now we're running out of time a bit. I'll save one question for next lesson. Or for the start of the lesson. This is the actual question which I haven't done. For anyone who's doing this via YouTube or whatever, I'll just put what you have to do. Now that gives you a clue. You have to do the probability that x, I don't want 7, I want 3, 4, 5, 6. I want less than or equal to 6 minus the probability that x is less than or equal, not 3, but 2. Get your head around that. That's quite complicated. So that's because I want 3, 4, 5, 6. I don't want the numbers less than 2. So anyway.